Alright, so here we are with our 6-1 assignment. So we're talking all about vectors, and so remember that you can use this formula sheet, and most of what we're doing in this first section will be in the top of the formula sheet. So let's see, we're going to prove that RS and PQ are equivalent by showing that they represent the same vector. And so again, that just means that they go in the same direction and that they have the same magnitude, kind of same slope, if you will. Alright, so in this first one here, we're going to do RS, and so R is the starting point, which is at 7, -3, and then S is at 4, -5. And again, looking at this image, we're going from R to S, and so our arrow is going to go that way. The next one goes from P to Q, and P is at 0, 0, and Q is at -3, -2. And so hopefully as you're looking at this, you can see that their magnitude would be the same because they both go down 2 over 3. And so we do know that they would have the magnitude of the square root of 13. And then, again, their arrows are going in the same direction. So, same path of down to left 3. And then we also have same direction. And technically same magnitude as well. So, all right. And again, that magnitude was square root of 13 from 2 squared, and 3 squared would make 14, and then, 13, and then square rooted. Alright, this next one, they want you to do the same thing, so we're going to plot 2, 1, so that's there, and then that's traveling to 0, -1. So down 2 over 2. And then the next one is going from P to Q, so P is at 1, 4, and Q is at -1, 2. And so again, they're having the same path of down to left 2. They also have the same direction because that arrow is going in towards the bottom left. And then they actually have the same magnitude as well because you would end up doing 2 squared and also 2 squared again. Adding those together would be 8, so square root of 8 is their magnitude. Alright, the next one, let P and Q and R and S be this, and we're going to find the component form and the magnitude of the vector. So again, component form, looking at our directions, tells us that we can do this head minus tail idea where we subtract the x's and then subtract the y's, and that becomes our component form. And then the magnitude, of course, would be to take those component pieces and square them, and square root, as I was just doing in the previous problem. So we're having Q to R, so Q is 3, 4, and R is -2, 5. And so it's going from Q to R, so that's this way. And so we can either transform this and understand it, or we can transform it to the 0 and then kind of get the component form from that. But actually, I'd rather do it the other way, which is a little easier than subtracting. I guess the first time I'll do it, I'll subtract, because why not? So Q is 3, 4, and so that means that x1 and y1 are 3 and 4. And then R is -2, 5, and so that's going to be your x2 and your y2. And so when we make our component form, we're going to end up with, let's see, x2, so -2, is that what it is? It starts with a 2, so, yeah. So 2 minus 1 and that's a 3. And then we're going to have 5 minus 4. Oops, 4 is supposed to be green. Okay, and so we'd end up with the component form vector of negative 5, 1. But again, you could have gotten that from the fact that this goes left 5, so negative 5, and up 1, so positive 1. Alright, so that would be your component form. And then the magnitude comes from the fact that we're going to be doing negative 5 squared plus 1 squared and then square rooted. And so our magnitude is going to be 25 plus 1 square rooted, or the square root of 26. Alright, so taking a look at the next one, we're going to do PS. So P is at negative 2, 2, and S is at 2, negative 8. Ooh, that's very down there. Okay. So P to S. And so if I look at my horizontal movement, I've gone 1, 2, 3, 4 squares to the right, so positive 4. And then we've gone 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 squares down, so negative 10. So you don't necessarily have to do this whole subtraction idea, but if you don't have a grid, it's a lot easier to do it with the subtraction. And then, of course, our magnitude is going to come from 4 squared and 10 squared, being square rooted. And so we're going to have the square root of 116 for the magnitude. Alright, then our next one is 2QS. Okay, so where's Q to S? 3, 4. And 2, negative 8. So 3, 4. And 2, negative 8. And so that's QS, so let's go ahead and find the component form of that. So it's left 1, which means negative 1, and down, let's see, 4 plus 8, so negative 12. But then they want you to multiply that by 2, and so our form is actually going to be negative 2, negative 24. Alright, and then the next one, for our magnitude, you're going to get negative 2 squared and negative 24 squared and square rooted. So 4 plus 24 squared. It's like 600 something. Oh, 576. Okay. And so square rooting that, we're going to get the square root of 580. Alright, ooh, and then the last one. Wow, that's a lot going on. Okay. So QR is 3, 4 to negative 2, 5. So 3, 4, negative 2, 5. Okay. And so that component form is going to be negative 5 and then up 1. So negative 5, 1. But we're supposed to multiply that by 3. So we're going to get negative 15, 3. Okay. But to that, I'm going to add PS. And so PS is going to be, where's P? Negative 2, 2. And S is 2, negative 8. Alright, and so the component form of that is, let's see, over 1, 2, 3, 4, so 4, and down 2 plus 8, so down 10. And so together, putting those in addition, we're going to get negative 11 and negative 7, adding them up. that's the component form of this together. And then, of course, the magnitude is going to be the two values squared and added together and square rooted. So 11 squared is 121 plus 49 from 7 squared, so it's the square root of 170. All right. Just checking that those were all the answers everybody else got. Yes. All right. Anyway. So, in number 13, we're going to have the u vector being negative 1, 3. The v vector is 2, 4. And a w vector, which is 2, negative 5. So, as I showed in the previous one, to add vectors, all you have to do is add their component forms. So if u is negative 1, 3, and v is 2, 4, you just add their component pieces, and you get 1, 7 as your answer. Alright, the next one, we're going to add, u and v, and we're going to, u and w, and we're subtracting them. So u is negative 1, 3 in component form, and w is 2, negative 5. And then we're going to subtract them, which is the same as adding. We're just going to go subtracting. So negative 1 minus 2 is negative 3. And 3 minus 5 is negative 2. So that's our solution to number 15. The next ones take a little bit more because they're having you take, for instance, 2 times negative 1, 3, and then adding that to, 3 times 2, negative 5. And so officially we're going to actually be taking negative 2, 6, and adding it to 6, negative 15. And so if we add those, we get 4, negative 9 as our answer. And then the last one, let's see, negative 2 times negative 1, 3 as our u vector. And then we're going to subtract 3 times our v vector. And the v vector is 2, 4. And so officially, if we're going to subtract those, it becomes 2, negative 6. That will be subtracted with 6, 12. And so our answer becomes 2 minus 6, which is negative 4, and negative 6 minus 12, so negative 18. Anyway, showing lots of the steps for that one. Alright, so next one we're going to find a unit vector, and so hopefully we remember our unit vector is taking the component form and dividing by its magnitude, and then it also wants the direction angle of the vector, so that's that tangent inverse of b over a. So in part u, I want to find the magnitude, the first part, so I'm going to take negative 2, square it, add it to 4 squared, and square root. And we're going to get 20 square rooted, which means that the unit vector is going to be negative 2 over the square root of 20, and then 4 over the square root of 20. And then the direction angle is going to be tangent inverse of 4 over negative 2. Because b, as the formula says, is the second, or the vertical movement of the vector, so b over a. And so if we take our tangent inverse in degree mode of 4 over negative 2, you end up with negative 63.43 degrees. And that is within quadrant 4, so we're good with not adding or subtracting stuff. The next one looks different, but remember this is just the different format for component form. So this is -1 technically and -2, because your I column is this value and your J column is this value. Alright, so to find the magnitude of W, we're going to take -1 and square it, and add it to -2, the quantity squared. And so we end up with the square root of 5 as our magnitude. And so therefore the unit vector becomes -1 over the square root of 5 and -2 over the square root of 5. And what does that mean for the direction angle? We're going to do tangent inverse of A, which is -2, over B, which is -1. And we get positive 63.43, which again is in quadrant 1, and so that's where we keep it. Okay. Moving on, we want to find a unit vector in the direction of the given vector and write your answer in a component form and as a linear combination, so just with those i's and j's next to it. So we're finding a unit vector in the direction of the given vector. Alright, so here we are with our unit vector. So our unit vector is going to be the magnitude, so forgot my symbolage here. Comes from the square root of 2 squared and 1 squared, so the square root of 5. Alright, so in part A, the component form of the unit vector is 2 over square root of 5, and then 1 over the square root of 5. And then the linear combination of the standard unit vector idea is just going to be those same numbers next to an I and a J. So 2 square roots of 5I, and then plus 1 square roots of 5J. And I guess you could get a decimal or you could rationalize the denominator, but that is not the main point here. Alright, in the next one, we need our magnitude again, so we're going to do the square root of -4 squared plus the square root of -5 squared. And so we have 16 plus 25, which is 41. So the square root of 41 is going to be our denominator, so -4 over the square root of 41, and -5 over the square root of 41. And then for our linear combination, we're going to have -4 over the square root of 41 with an I next to it, and then I guess we can do minus because we're subtracting the 5 over the square root of 41, and then a J. Alright, let's see. Now we're going to find the component form of the vector given that we have its magnitude and its angle. So taking a look at our formulas, we've got, well, that's obnoxious, but it comes from the angle times, which one is it, cosine? Oh, sorry, no, the magnitude. Times the cosine of the angle, and then the magnitude times the sine of the angle is going to be your component form given an angle and a magnitude. So, going back to this one, we're going to do 18 times the cosine of 25, and then 18 times the sine of 25. And of course you could do this using just regular trig, but it's nice to be able to do it that way. So our component form becomes 18 times cosine of 25, so 16.31. And then 18 times sine of 25 in degree mode is 17.61. Alright, and the same goes for the other one, so it's going to be 47 for the magnitude times cosine of 108, and then 47 times sine of 108. And so we get 47 times cosine in degree mode, and then also sine. So our x value becomes negative 14.52, and then 44.70. Alright, and then the next one, they want you to find the magnitude and the direction angle of the vector. So our magnitude, again, is just taking the first part of the component form, squaring it, and taking the second part of the component form and squaring it. So we'll have 9 plus 16, or 25 in a square root. So, woohoo, 5 for the magnitude. And then the direction angle is going to be that theta, and it comes from tangent inverse of the B piece, which is the vertical movement, and then the A piece, which is the horizontal movement. So we do tangent of 4 over 3. Oh, sorry, inverse tangent. Which hopefully reminds you of, again, just kind of setting up a right triangle and then finding the angle that we're looking for. And so we get 53.13. Alright, so the next one, we're going to find the vector with the given magnitude and the same direction as u. Okay. Well, in order to get this new vector, we're going to need to find the angle of u, because then we'll know what the angle of v is going to be. And so we need to take 3 squared and add it to negative 3 squared and square root. Oh, sorry, we're not finding the magnitude, we're finding the angle measure, which is tangent inverse of the vertical movement over the horizontal movement. And so our theta ends up being negative 45. So that means that if we're going to make the component form, we're going to need the vector length times cosine of negative 45, and then the vector magnitude times the sine of negative 45. And so our resulting vector is 1.41, and then 2 sine of negative 45 is negative 1.41. And so we'll do the same piece for the next one. So we need to find what tangent inverse of 7 over negative 5 is. And so our direction angle is tangent inverse 7 over negative 5 is negative 54.46. And so then when we make our component form, we're going to do the magnitude of 5 times cosine of negative 54.46. And then the magnitude again times sine of negative 54.46. And so our new component form vector is 5 times cosine of that value. So 2.91. And then 5 times sine of negative 54.46232221. Anyway, just put all the digits in. So negative 4.07. Alright, an airplane is flying on a bearing of 335 degrees at 530 miles per hour, and we need to find the component form of the velocity of the airplane. So, weird that they're saying of the velocity because 530 is that, but anyway, they've just mentioned it twice. So, we're going to do the same piece again because we know the magnitude. Is 530, and then we're going to multiply that by cosine of the angle that is given, and then 530 for the magnitude times the sine of 335. So let's see, 530 times cosine of 335, and then 530 times sine of 335. So our component form of the vector is 480.34 and negative 223.99. Again, just using that formula that I wrote up here, but is part of calculating. Oops, did I go to the end of that page? Yes. Alright, and then our last page here, we've got two more problems. So, an airplane is flying at a bearing of 170 degrees, and we need to find the component form again. Woohoo! So, 460 is the magnitude of the vector, and multiply by cosine of 170, and then 460 times sine of 170. Look at us calculating. Okay, 460 times cosine of 170, and 460 times sine of 170. Boop. So we get negative 453.01, and then 79.88. Alright, on the last one, the airplane is flying at a compass heading, okay, of 340 degrees at 325 miles per hour, and a wind is blowing with a bearing of 320 degrees at 40 miles per hour. So basically what it's saying is that, as in our example for the notes, we need to add the two component form vectors. And then we'll see where the plane is heading. So remember that ground speed is magnitude. So what we're going to do first in part A is find the component form. So that means that I'm going to take 325 times cosine of 340 and 325 times sine of 340, and add that to the other one, which is 40 miles per hour, and cosine of its angle, and sine. So we're going to add those together. However, in order to add those together, I need to actually just solve them first. So 325 times cosine of 340 is 305.40. And then the next one with sine is negative 111. And there's our next one, so we'll add them. So now we've got the actual one, and now we're going to find its magnitude. So we'll take the 336.04, square it, and the other piece, square it, and take the square root. So that's 362.84 miles per hour. And then to find the direction angle, the tangent inverse of the second piece in the component form over the first piece. And so we get a direction angle of negative 22.16 degrees. And there you have it. So that is the 6-1 assignment.